This next example is going to reveal an advanced technique, something that comes up occasionally on these related rate problems, and that is you don't have enough information. So what you have to do is you got to be clever about it. You got to substitute something away so you don't have to deal with it. Exercise 11. A water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 centimeters. Hey, look at this. I don't actually have a picture. I'm going to draw one. So I've got an inverted cone, which will look sort of like this. There we go. Looks pretty good. And it has a base radius of 2 and a height of 4 here. So that's supposed to be 4. And this isn't changing, right? This is forever. And you know what? I'm going to add some shading here. And apparently it's yellow is the color that I'm using today. Do you remember from geometry, solids of revolution? It's this right triangle that you'd revolve that around an axis in order to generate it anyway. Not that that matters. Actually, it does, because that is something that we're going to do some point this year. Let's see. I got all of those marked down. If the water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, a lot of stuff to process here. We've already written down, I'm not going to write down again the radius and the height of this cone, but what's the next number? It is 2 cubic meters per minute. And notice that it just says water is being pumped in. Sort of like that balloon question. It doesn't mention volume, but I'm going to get the implication that it's volume because it does say meters cubed per minute. Volume is equal to 2 m cube minute. All right, so as we start filling this cone with water, of course, the height of that water is going to increase. So is the radius, right? The radius is also going to increase. Sounds like a related rate problem to me. Okay. What? I put V. This should have been dV dt. This is the rate. Good thing I have you guys here to point these things out to me. Find the rate at which the water level is rising. dH dt, right? This thing. Well, we'll say, I don't know what I'm doing over here, but we'll say that we have the water level that's rising here. That's going to be our height. dH dt is equal to a big fat question mark. Okay, and when the water is 3 feet deep, so H is equal to 3 feet. When, there's that key word again, when it happens. This means, once again, that this never goes in until after we differentiate. Not before. Okay. All right, so I've gotten everything that the question gives me. Is it enough? No, it's not, as we will see. But maybe you don't know that. Maybe you don't know that whenever you're working a problem like this on your own, especially under the, the time situation of a test, a quiz, real life. I need an equation that's going to relate all of these quantities together. And we are talking about the amount of water that is in a cone. That's the volume of a cone. Volume of a cone is 1/3 pi r squared h. Now, don't worry if you didn't remember that particular formula. I have it on a pretty good authority that they will provide that formula for you, because it's not supposed to be about recalling geometry information on some level. It's supposed to be a calculus exam. So anyway, they will give that to you if you need it. Okay. Problem. Do you see a problem? It has a radius in here. The only radius that we have is the radius of the whole conical tank. We don't have the radius when this is at 2 feet. I don't have a particular volume so that we could solve for it. This is an issue. Notice that we're looking for a dH dt, but when I take the derivative of this implicitly with respect to time, you're going to introduce a dr dt. I don't have it. and I don't have a convenient way to find it. So what do I do? And this is where some more geometry comes in. What I'm going to do is I'm going to draw another little triangle in the picture here. Doop, 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 doop. Here's our radius, and here's our height, specifically of the water. So maybe I color this one in blue. That's changing, of course, and I don't know like what it is at any particular moment, except for the height at 3. Now look at these two triangles that I've drew in here. The blue one that's down here on the bottom, that sort of looks green because it's on top of yellow. And then the yellow one. What type of triangles are they? Besides being right, they are similar triangles, right? Because when you have nested right triangles, these angles matched up. The right angles are the same. So in terms of geometry, that's the angle similarity, which allows those two triangles to have proportional sides. And that's what I need to know. I'm going to set up a ratio. The radius to the height should be equal to this 2 to 4 all the time for this cone. So off to the side here, I'm going to write that radius to the height is equal to 2 over 4. Now, I've got a system of equations, and I've got to decide what I'm going to solve this for, because I'm going to substitute it in there. Remember, we need to get rid of the r. We need to get rid of it altogether because we don't have a dr dt, and we don't have the radius at that particular time. Now we have an equation where we could very easily solve for it. What is there in h on the bottom of it? What the heck? That should have been a 4. I wonder, let me rewind the video. Did I say 4 and write h? Because I do that sometimes. But just with 4 and h's. Okay, so which variable are we going to solve this for? I'm going to solve it for r, because if I solve it for r, I'll have some expression that contains h's, which I can stick in here, and I'll have only h's, no more r's. So let's multiply this h over to the other side and simplify the fraction. R is equal to 1/2 of h. Let's take that and substitute it in for this r right there. No, that's so ugly. It's not what was supposed to happen. This is what's supposed to happen. That looks far better. Carrie, like you do any aesthetic test that you want to. That one looks better than the other one. So let's do our substitution. 1/2, 1/3 pi. Instead of the r, we're going to write in our, I'm going to write that as, I guess, h over 2. Why not? Squared times the h. And voila, there's no radius in it anymore, but let's go ahead and simplify here. So inside the parentheses, I'm going to have an h squared over 4. The 4 there is going to multiply by the 3 here, give us a 12th. 1/12 pi. H squared times this h cubed. Now we are ready to take the derivative with respect to time on both sides. On the left, we have a dv dt. And on the right-hand side, let's leapfrog the 3 down. 3 over 12 reduces to a 4th, I believe. Pi, r squared, h squared, and then chain rule it, dh dt. And look, no radius to worry about, no rate at which the radius is changing, which I didn't have. Don't have to worry about it now. Now, all I have to do is plug my stuff in. dv dt is equal to 1/4 pi. I'm going to write that as pi over 4. You know, like it's pre-cal or something. My h, was it a 3? I think it was a 3. 3 squared. And then the dh dt was... Dang, that's what I'm looking for. Okay, dh dt. So here's an instance where what I can do, what did I just do? I don't even know. Okay, here's an instance where I guess I can go ahead and plug all this stuff in dH dt. And then solve for the dH dt numerically like this, instead of solving first and plugging it in. You can do it in either order, and you should still get the correct answer. That's right. I planned this all along, just to show you an alternative method. All right, so I'm going to plug 2 in for the dV dt, so a 2 over here. Okay, so let's solve that for dH dt. I'm going to multiply by the scribble. I'm going to multiply by the reciprocal of this. That's going to put an 8 up here over pi. So I got 8 over pi is equal to 3 squared 9 dH dt. What a mess. What an absolute mess, dH dt. Okay, and then divide by the 9. And it's going to go down on the bottom with the pi. So I have 8 over 9 pi dH dt. Hey, what are the units on this? Here, let's think about the units this way. This is the height which is changing. Our height is being measured in feet. And this is our time which is changing, which is being measured in minutes. Feet per minute. Okay. All right. So at the instant when the height of the water in the cone is 3 feet, then the height is increasing at a rate of 8 over 9 pi feet per minute.